Well, good afternoon. It's 12:17, 2 minutes late starting the Cal 3 class, which is Math 227. However, I'm the only one in the room, so I guess we'll get started from here. All right. Just in ways of announcements, let me remind you of these facts. Okay. Number one, the research paper, only 3 of the, I guess it's now 1, 2, 3, 4, 5. 3 of the 5 of you have turned in a research paper. It'd be great to have the others in. If you get it in this week, you still get that 1 remaining bonus point. If you turn it in next week, you just get your score. After next week, you start losing points, so please get your research papers in this week or next, preferably this week. Okay, now that I look at this, it looks like every one of, no, I'm sorry, that's not quite right. 1 person still has not turned in test 1, so please get those in as soon as possible. And test 2, only 1 person has turned in, so the other 4 of you, please get those in as soon as possible. All right. Can't think of anything else, so let's get going where we left off last time. We're ready to start the second partials test, except we still had example 2 to do. We got example 1 done on page 942, but we didn't, and we did, there was example 1. So let's do example 2 on the same screen. Okay. Sorry about my throat. I picked up a sore throat over Thanksgiving. I was around a bunch of grandnieces and nephews, and basically at least 2 or 3 of them had runny noses or one thing or another. So may have picked up a pretty, a little bug from a little person, and my wife is sick, but so far, knock on wood, I haven't gotten sick with it, but I do have a sore throat, a little bit of drainage. So anyway, here's example 2. Finding a relative extremum. Determine the relative extrema of this function, f of xy, is equal to 1 minus x squared plus y squared to the 1/3 power. X squared plus y squared to the 1/3 power. Okay, now, a little bit of review of what we covered last time. When you're looking at extremum, think a lot like you did when you're looking for max and min, extremum in, basically 2-dimensional calculus. In other words, 1 independent variable, 1 dependent variable. What was the first thing you did? Take a derivative, okay? And so what we do in this case is take a partial derivative and take both partial derivatives, okay? So first thing we'll do is f sub x of xy is equal to, well, 1 doesn't produce anything for you. That's a 0. And then you have a minus 1/3 x squared plus y squared to the negative 2/3 times, chain rule, a 2x. Okay? And if you put all that together, that's a negative 2x over 3 times x squared plus y squared to the 2/3 power. If you put it in the denominator, losing the radical there. Okay? Now, what we're interested in with the first derivative in the 2-dimensional case, or might only say a 1-dimensional case, a single independent variable, single dependent variable, well, you were looking for where that first derivative was 0. Well, we do the same thing here, and the only place where it is equal to 0 is at x equals 0. So this is equals 0 at x equals 0. Doesn't matter what y is, okay? So let's do our f sub y of xy, and that would be, going back to the original there, that would be, again, negative 1/3 x squared plus y squared times chain rule, oops, okay, to the negative 2/3 times chain rule 2y, okay? And again, putting that in perspective here, that would be a negative 2y over 3 times x squared plus y squared to the 2/3 to get it out of the, it is a 3, it doesn't look much like a 3. And where is that equal to 0? That's equal to 0 at y equals 0. So it looks like x equals 0, y equals 0 is your critical point, okay? And both of those partial derivatives exist for all points in the xy plane, except for the point x equals 0, y equals 0. Why? Because at those points, your denominator becomes 0. It's okay for x to be 0, that's okay, or it's okay for y to be 0. But if they're both 0, then your denominators for both of these cases go to 0, okay? So, we see in the first place that where x equals 0, y equals 0, which you think might be a critical point, but it doesn't exist there, okay? But then on the other hand, it's where your derivative either is equal to 0 or does not exist. Well, they don't exist at 0, 0, so that still keeps it as a candidate for your extremum, okay? Well, let's see what happens when we plug that into the original function. F of 0, 0 would be 1 minus 0, right? So that would just be 1. So it looks like the point where x equals 0, y is equal to 0, and z is equal to 1. That is on the curve. It is defined there. Even though the first and second partial derivatives are not defined there, that makes it a good candidate for a critical point, okay? Now, the other issue, if you look at any values of x close to 0 but not 0, for instance, let's just take 1, f of 1, 1, say, that would be 1 minus some positive number, the cube root of a positive number. Well, cube root of a positive number is always positive. So, guess what? You're subtracting some, and it can be a very small positive number from 1. That means it never gets greater than 1, okay? So, therefore, it's a maximum. This point is your critical point, and it turns out being a maximum. Maximum, okay. And it's an absolute maximum. It's a relative maximum for sure, but I believe it's also absolute. Okay, now, the interesting feature here is, as we saw, f sub x is 0 for all values x equals 0. But f sub y is not a 0 there, and f sub y is equal to 0 except at y is equal to 0. F sub y is equal to 0 at y is equal to 0, but f sub x's are not there except for x equals 0. So therefore, the other values where f sub x is equal to 0 and f sub y is equal to 0 are not relative extremum. Okay? Now their graph here I'm having difficulty seeing that the F sub they're saying I'm not seeing according to their graph here. Let me just look on something else. And it's just maybe my viewpoint here, and indeed that may be the case, but their graphic here, I don't see how f sub x of xy is equal to 0 for all values x equals 0. X equals 0. It's up and down the y-axis. F sub x. Oh, those still don't see it by their graphic here. In fact, their graphic doesn't quite look correct, but I guess it is. The it just, yeah, it's hard to see on a three-dimensional, try to do a three-dimensional plot in 2 dimensions. It's really hard to see, but I guess that could be the f of that. It says it is, and it works out that it is. But those, it is required that either both, if you go back to the definition of a critical point, it's a critical point if both your f sub x and f sub y are equal to 0 at the same point, or either f sub x or f sub y does not exist at that point. Those are your critical points. So it's not an or for the first or an and for the second. It's an and for the first and an or for the second. So that's all there is to it. We've done it. I've answered all they had. Excuse me. So let's now go to, sorry, now I've got the hiccups. The second partials test. Okay. Theorem 1316, which we had on the previous page, the relative extrema occur only at critical points. But that doesn't say at all critical points you get a relative extremum. Not that. The only place that extremum can occur are at critical points, but not all critical points are extremum. Okay? And that's what Theorem 1316 tells you, that to find the relative extremum, you need only examine values of f of x, y at the critical points. However, as it is true for a function of one variable, the critical points of a function of 2 variables do not always yield a relative minimum or maximum. Okay? And in 2 dimensions, those are called saddle points. And they give a well, here's what I just read. Neither relative maximum or relative minimum. And here's a picture of one. As an example of a critical point that does not yield a relative extremum, consider the hyperbolic paraboloid shown here. Okay, we remember those from before. Y squared minus x squared. Okay. What's the critical points? It's where f sub x of xy, which is equal to minus 2x, and that would be 0 at x equals 0. Okay, and f sub y of xy would be 2y, and that's equal to 0 at y is equal to 0, and only, well, there is the point. Now, again, I find this graphic not particularly useful, okay? And then if you took that critical point, 0, 0, and plugged it in here, this is equal to 0 at x equals 0, y equals 0. Okay, so that value, your z, would be 0, and that's why they say 0, 0, 0. Now, what I don't like about this graphic is that appears to be the origin right there, and this isn't directly over the origin, or at least it doesn't appear to be. Okay, it looks like the graphic is a little off kilter from where the axes are, or either the axes are not under properly where they should be in the of the graph, one way or another. But you see what's happening here, and this was characteristic of a hyperbolic paraboloid, is that your keep wanting to say contours. It's sort of like them, but you don't call it that. Your level curves. That's it. Level curves in the let's take the XY planes. Those would be the curves that are doing this number here and this number here, I think. No. Maybe they don't show the level curves in that plane, but they would be, that's the hyperbola part of it. The parabola part would be, look at the YZ planes or any plane parallel to that, that forms a parabola. But look at the ones in the XZ plane, and those form parabolas. But in the XY plane you have, but the one parabola is opening upwards, the Z is equal to Y squared is opening upwards, and the Z is equal to minus X squared is opening downwards. So therefore you have at the vertex of both of those, the common vertex is 0, 0, and in this case the Z would be 0 as well, and that's opening upwards in the XY plane, a parabola opening upwards there, and a parabola opening downwards in the XZ plane at the point 0, 0, 0. So that is indeed a saddle point. One set of curves is the maximum point, and the other is the minimum point, and it's not going to be an extreme point, local or relative max or min, over the whole curve. Okay, I think we kind of beat that to death. At the point 0, 0, both partial derivatives are 0, which makes it a critical point. Function f does not, however, have a relative extremum at that point, because in any open disk centered at 0, 0, the function takes on both negative values along the x-axis and positive values along the y-axis. So the point 0, 0, 0 is the saddle point of the surface, neither max or min. So here's theorem 1317, which kind of combine some of the earlier ones with this. So here's what we have, the second partials test. Let F have continuous second partial derivatives on any open region containing a point AB, for which f sub x of AB at AB and f sub y at AB are both equal to 0. To test for relative extrema of x, consider this quantity. It's kind of like your discriminant was in the quadratic formula. Excuse me, I had something stuck in a tooth. Okay. If you look at just that discriminant by what sign it is, or what or what value it is, that lets you know something about your solutions. Well, this one, the D, which I don't know if they use that to represent discriminant or what, but this discriminant is the product of your second derivatives with respect to x, f sub xx at AB, times f sub yy at AB, minus f sub xy at AB squared. Okay? Now, if that D is greater than 0, in other words, a positive number, now you know that f sub xy at AB squared is going to be positive. So in other words, this is saying the product of f of xx times f of yy has to be greater than the square of the cross partial, the square of the cross partial, I guess is the best way to name it. If D is greater than 0, that means your product of the two second partials, first with respect to x and both with respect to y, if that product is greater than the square of the cross product, f sub xy at AB, then D is positive. And you have to say and f sub xx is positive. Then f has a relative minimum at AB. So in other words, the product is positive. Not quite product. That difference is positive, and f sub xx is positive. Okay? Now, that also implies that f sub yy has to be positive as well. Because if f of xx is positive, then f of yy must be positive. Otherwise, if it were negative, then you'd have the product of f of x and f of xy would, f sub yy would be negative, and you're subtracting off a positive number. That would be a very negative number. Okay? Then f has a relative minimum. Now, if D is greater than 0, but f sub xx is less than 0, that means that f of xy has to be negative as well, because you'd have to have a negative times a negative to make a positive. And you have to be positive, subtract the positive off, and the D, which is the difference of the two, be positive. Then that's a relative minimum. So if your f sub xx is positive, that implies f of yy has to be positive, and in other words, it's opening upward along the x-axis and opening upward, so to speak, in the y directions as well. That's what it means by f sub xx. Positive concave up, you might think concave up in both cases. Then you have a relative minimum. But if D is positive, the difference is positive. And f sub xx is negative, that means it has to be that f sub yy is negative, so therefore you have a relative maximum at AB. But if D is negative, then AB, f of AB, is a saddle point. Okay? Now, what does that mean? That means that the if D was negative, that means that either one or the other of alpha of xx and alpha of xy is negative, because then subtract from that I keep wanting to say cross product. That's not the right term. Mixed partial. Mixed partial is the thing you call that. Or just that the mixed partial squared is greater than the product of the other two, whether they're positive or negative. Then that's the saddle point. The test is totally inconclusive if d is equal to 0. You can't tell what's going on there. Okay, I guess we beat that to death. Now, they say something here that, yeah, it makes sense. It says a convenient device for remembering this is to write the determinant. And D is a pretty decent thing to do. The determinant of F sub xx, F sub xy, F sub yx, F sub yy. Okay? Now they're, of course, all at the same point. Let's just call it AB. Okay, and that determinant would be the product here, the downward product, which would be F sub xx at AB times F sub yy at AB minus F sub xy squared at AB. Because these two are equal to each other. So it doesn't matter which order you write the partials. Okay? And that would give you exactly that phrase. All right. All right, let's use that. This is example 3. I think someone is arriving. All right. Good to see you.
Doing all right?
Doing well, thanks. How about you? Okay. Can't think of anything special I may have said, but on a couple of lights here. I'm moving kind of slow. Let's project the light. And I'll get the overhead light, even though the sunshine's coming through nice and brightly. Yeah. Earlier this morning, there was no heat in the room, but it was still okay, a little on the cool side. This box was not working at all. The box is still not working at all, but it never gave you a chance to adjust anyway, so it doesn't matter. But at least I can look at it and tell what the inside temperature was, what it was set for. Now I know nothing. But anyway, at least we got heat. This morning I checked, no air at all coming out, so we're just ambient. But then they came and worked on it while I was teaching the first time, which made a lot of noise, and not a lot, but some noise. And then before my second class, I got up there again, and sure enough, it was coming out. Okay, we're on page 944. This is chapter 13, functions of several variables. We're at 13.8, extreme functions of two variables, and I just done. I did example 2 and talked about the second partials test, and that's what we're doing in example 3. So here is the function f of xy is equal to minus x cubed plus 4xy minus 2x squared plus 1. Now this isn't any shape that we're familiar with, or at least that I'm not familiar with. You may be, but I don't know. All right, so we want to find relative extrema. Okay, Well, what was the test for relative extrema?
Did you say what now?
How do you go about finding your relative extrema, which could be a relative minimum, relative maximum, or whatever? Okay, f sub x. The partial of f with respect to x at xy, and what is that equal to?
Negative
3x what?
3x
Squared. Exactly. Next. Plus 4y. Yeah. And then the rest don't contribute anything. Okay? Now, we want to know where that partial is equal to 0. Okay? Well, that's going to be anywhere on a parabola-like shape in the xy plane, which is opening downwards in the x. So we'll come back to that. Okay? But what we must consider is what? F sub y. And the values here. And what would that give us? Where? Okay. Positive x. Where you get that?
From the negative 8, so you keep the negative 8.
Okay. Yeah, going up here, when you take the partial with respect to y, you treat x as a constant. So that doesn't contribute a thing. It's a 0. Okay. How about the next term? For x minus 4y. Perfect. And you set that equals 0. Well, obviously, you can factor out a 4 there and just have x minus y equals 0, or x is equal to y. So anywhere where x is equal to y, there is going to be where your where your derivative with respect to y is equal to 0. Okay, anywhere on the identity function, line, that diagonal line there. We'll take that value and plug it in up there in the f sub x, because they both must be 0, or they both must not exist. Hey, guess what? They exist everywhere. So the thing about them not existing, that's not a question here. So plug this in here, and you get minus 3x squared plus 4x, if x equal y, is equal to 0. That would be true at 2 places. Factor out an x, and you have minus 3x plus 4 equals 0. So that would be true at x equals 0, or at minus 3x plus 4 equals 0, which would be where I'm going to rewrite it as 3x minus 4 is equal to 0, and add 4 to both sides, and get 3x is equal to 4, x equal 4/3. Okay? So, but x has to equal y, so there's 2 places, at 0, 0, or at 4/3, because x has to equal y. Okay, so there are 2 points in question. Let's go back to our original function and see what we got there. F of 0, 0 is equal to 1, right? And f of 4/3, ooh, that's going to be a lot worse. That would be a minus 4 cubed is 64 over 27 plus 4 times 16, and 4 times 16 is 64 over 9, I believe it is, isn't it? Yeah. Okay. Minus 2 times the square of that, and that would be 16 ninths, and twice 16 ninths would be 32 ninths plus 1. Okay, let's call that 27 over 27, okay, because we're going to have to get everything to 27ths anyway. So this is minus 64 27ths plus, goodness gracious, do I want to do this? 3 times that would be 192 27ths minus 96 27ths plus 27 27ths. Okay. Add the two negatives together, and that gives you negative 150. No, yeah. Negative 150. Goodness, what a pain in the neck this is. Negative 150, and you have a plus 219. That would give you 69 27ths. Okay. 69 27ths is greater than 1. So just right now, I'm guessing that the second one there, 4/3, 4/3, is going to be a relative maximum. And 0, 0, I'm not sure it's going to be a relative minimum or not. And it could be neither one of them are. So,
Why did you split it? Why did you do the 4/3?
okay. This one told us that x has to equal y, right? Right? This one. Second derivative, the first derivative with respect to y gives us this, and that's only true when x is equal to y, right? Okay. This one up here had this weird form. That has to equal 0. But if x is equal to y, you can plug in, instead of y up here, plug in an x. And that gave us that value. And then when we factored it out, this one gave us x equal 4/3. But x has to equal y, so y has to equal 4/3. You see that? So, we know that at the first critical point is equal to 1, the second critical point, something greater than 1. In fact, a little bit greater than 2. 2 would be 54 27ths, and this is 69 27ths, which would be 15 27ths more, which actually we can reduce if I'm doing my math right. 2 and 15 27ths, which would be 2 and 5 ninths. So something a little bit more than 2.5, not quite 3. Okay, so that's the value of alpha at the second, which could be a relative maximum. The other could be a relative minimum, but in order to tell, the easy thing to do, relatively speaking, is calculate your partials, okay? Your second partials, okay? So the first one here we'll calculate is alpha sub xx at xy, okay? And what is it? If this is your partial of alpha with respect to x, what's the second partial of alpha with respect to x? negative 6x. Okay? We'll also need f sub y. My pen is really slow at xy. So let's do the partial of that. Negative 4, isn't it? Negative 4. Okay? That is a 4. It looks sort of like a 9, but that's a 4. That's more like a 4. Okay? And we'll need to do our cross mixed partial f sub xy at xy. Okay? Now, it should be we get the same thing both ways. That's a good check. Goodness gracious, where is this going? Okay. So first let's do f sub xy, which take the partial of this with respect to y. Partial of this with respect to y, and what do you get? Four. Let's also, just for funsies, take f sub yx at xy. So take the partial of this one with respect to x. And what do you get? 4 again. So yeah, those are equal. So that's my little check to make sure we did things right. And we did, because those have to be equal to each other. Okay? Okay. Now, our second derivative test, second partial test. You flip back one page, and it tells you what your D is, and I just don't have a lot of room to write. Let me see if I can write it up here and make it make sense. D is equal to f sub xx times f sub yy minus f sub xy squared. That's shorthand. They put a lot more things in it. Since I'm running out of room, let's just do that. Okay, well, what's your f sub xx? That was minus 6x. Minus 6x. And your f sub yy was a minus 4. So that would be a plus 24x. I'm just running out of room. That's why I'm trying to do it all in one spot. Okay, so it's plus 24x. Okay, minus f sub xy squared. Well, f of xy is 4, and 4 squared is 16. Okay, so there's your discriminant. Okay, let's evaluate it at our two critical points, 0, 0. When x is equal to 0, at 0, 0, your discriminant is equal to minus 16. That's negative. Okay? If your discriminant is negative, then you have a saddle point. So at 0, 0, you have a saddle point. At one place it's curving down, the other place is curving up. Not going to be a relative minimum or maximum. Okay? So that one's out of the play. Let's do it at 4/3. Okay? At 4/3, your D is equal to, and again, this product is it's 24. So it's 24 times 4/3 minus 16. Well, 3 will go into 24 8 times. 8 times 4 is 32. So you got 32 minus 16, which is positive 16. Okay? So your D is positive, greater than 0. Now we look at the f sub xx. Okay? And f sub xx at 4/3 is minus 6 times 4/3, and that would be minus 8. So here your f sub xx is negative, so that means it's a relative maximum there, which is what I sort of was guessing anyway, because it has a greater value than the other. Of course, it could be, that could be a saddle point, and this could be a minimum, or it could be this is a minimum, that's a maximum. It may not be very likely that way, but it could be. So sure enough, once we found out this was a saddle point, almost, not quite guarantees, but at least it suggests that could be a maximum. Certainly it couldn't be a minimum, because that's even less than it. So it's either another saddle point or it's a maximum. It turns out to be that's a maximum. Why? Because your f sub xx was negative, but your d was positive. Okay? D has to be positive for it to be a relative extremum. Okay? And if f of xx is negative, is positive, then it's going to be a relative maximum. If it's negative, it's going to be a relative minimum. Okay. So let's see if we got it right. All right. Oh, they have it. Okay. So let's clear my ink out of here. Do you need it any longer?
Yeah.
Okay. Let me get this out of here. Whether you can make any sense of that, I'm not sure, but I'll let you give it a shot. Okay, and you can go back and listen to it on YouTube when it gets out there. Okay. So let's see how they do it. Begin by finding the critical points. So how do you find the critical points? Take your partials. Partial of f with respect to x is minus 3x squared plus 4y. Partial of f with respect to y is 4x minus 4y. Okay, those partials exist for all values x and y, so the only critical points are those for which both the first partials are 0. Okay, now, if that was what you were given, and this didn't turn out to be something so easy to deal with, this might be a really tough problem. Okay, if you have to deal with a quadratic here and a different kind of quadratic here, that could be messy. Okay, but with that second one being something that's pretty easy to deal with, if that's equal to 0, x has to equal y. That then gives you a way to locate those points, set your partial with respect to x equals 0 and the partial with respect to y equals 0. Okay? Like I said, that first one doesn't particularly tell you a lot that's interesting, a little bit maybe, but not a lot. The second one tells you x has to equal y. Okay? So you plug that back into the first one, and you can solve for x or y, whichever you leave out, and okay. Let's see. Okay. So the previous slide got you your 2 critical points. Okay. Let's go back just to refresh there. X. Okay. X and y both equal to 0. X and y both equal to 4/3. Exactly what we got. 0, 0, 4/3, 4/3. Okay. So next step is to take, as we did, the second partial of f with respect to x, after we were taking the first partial, and that gave us a minus 6x, just like we got, and the f sub yy was minus 4. Okay? And the cross product, or the mixed product, mixed partial, was 4, positive 4. Whichever way you did it, you got a plus 4. So now we use our discriminant, if that's what you want to call it, and we'll do it at the 2 points, 0, 0, and 4/3, 4/3. So let's start and find that at 0, 0. So when this is x is 0, L sub x is 0. When x is 0, this is negative 4. Okay? The 0 times negative 4 is 0. And L sub xy squared would be 16. 0 minus 16, that's less than 0. So that means you're going to have a saddle point there. No way around it. We had already plugged in and found out when x equals 0, y equals 0, your function was equal to 1. At the very beginning we did that. Okay? And that's the saddle point. 0, 0, 1. It's going up in one dimension, down in the other dimension. Okay? Saddle point. So let's do the same thing using the same values there for 4/3, 4/3. Okay? Yeah. And this was the hairy one as far as all the numbers went. Okay? It was a negative 8 times a negative 4 is a positive 32 minus 16, and that gave you exactly 16. Positive. The D is positive. Okay? So that means it's either going to be a relative maximum or a relative minimum. Which will it be? Look at your L sub xx. At 4/3, 4/3, that's negative 8. Less than 0, so you can conclude it's a relative minimum at that point, and after that is increasing thereon. All right. Now, let's see if we can figure out from the graph here. Here's your stop, the point at 0, 0, 1. Okay? In this dimension along when you're straddling the x-axis, that is a relative maximum. When you're on the y-axis, that's a relative minimum. See? So, therefore, that's the saddle point. Okay? At the other one, at 4/3, 4/3, your value up here was, what was it, 2.6 or something like that. I don't remember exactly the value, but it was something greater than, it was 2 5/9, I believe it was. 2 5/9 was the value there. Okay? And because your partial with respect to x is negative, and your partial with respect to y is negative, and that's a greater value than this, than this, which was 16. There. But it is a greater value than the square of that. Then you can conclude that as a relative minimum. No, relative maximum. Because of the second partial. The difference there is this is negative, but the D value is positive. So that makes it a relative.
Will the D value always be positive?
No, no. If the product of these two, well, we saw this in the last one. Here the D value is negative 16. If it's negative, it's a saddle point. If the V value is positive, then it's either a relative maximum or a relative minimum. Okay? If that f sub xx is positive, then it's a relative minimum. Relative minimum. If the f sub xx is negative, that means it's a relative maximum. And this turned out f sub xx was negative 8. already calculated up here. So that made it relevant. Now, the problem comes if your D is equal to 0. You can't tell what it's doing anywhere at all. So you have to depend on a graph or something else to let you know what in the world is happening if that D happens to be 0. It's hurting so badly. I don't know if I said it while you were in here. I was around kids all over Thanksgiving, great nieces and nephews, and a bunch of them had snotty noses. So we both got exposed. My wife is sick. I've just got a sore throat with a little bit of congestion. But so let's look at, let's look and see how, we just did. We saw how they did it. Now, they're skipping example 4 altogether. I thought at least they would have a little bit of verbiage there, but they're not. They don't even have that paragraph that's right below this. You see figure 1370 times, hey, there he is. Muhammad is here. Okay. Okay. It was very good. I eat way too much. I think I got on the scale this morning and I think I gained close to 5 pounds. Not good.
Pretty solid.
Huh?
Pretty solid.
Yeah. So that means for the rest of the time between now and Christmas, I need to be losing, and hopefully you can lose most of those 5 pounds back so I can gain them again at Christmas. Okay. So. Yeah, and then spend all next year taking them off. That's the normal secret, yes. What's that? Yeah, of course, every year. And then keep it until Thanksgiving and then blow it then. Right. Lose weight, lose weight, lose weight, lose weight, and then Thanksgiving gain it all back. Okay. So, there was example 3. Okay. Example 4, right below, if you find on page 944, that little red square near the margin of the page there, right-hand side of the page, this is the last thing said right before that red square. The next slide starts at the top of 945. They skip everything that's at the bottom of that page. Here's what it says. The second partials test can fail to find relative extrema in 2 ways. If either the first partial derivatives does not exist, either of the first partials does not exist, you cannot use the test. Because if they fail to exist, what are you going to plug in? You can't. Okay? Also, if the D is equal to 0, you can't tell anything. The test fails. In such cases, you try to sketch or some other approach, just as demonstrated in the next example. So that's what we're going to have to do without any visual support from the slide set. So let's do example 4 here. All right. Find the relative extrema of this function. F of xy is equal to x squared y squared. Okay? What would be your first step? Second? Well, find the first partial, okay, of xy with respect to x, and what would that be? Second? No, 2xy. 2xy squared. You count the y as a constant, so y squared is a constant. X is the only variable there, so y squared is like a constant. The derivative of x squared is 2x, so it's 2y squared x, or 2xy squared. Okay? Now, when you set that equal to 0, the only place that, well, places that could happen, that would be at x equals 0, which is the y-axis, or at y equals 0, and that would be the x-axis. So there's a lot of possibilities there for that one. If you do your f sub y at xy, what would that be? 2yx squared, or 2x squared y. Well, again, that's equal to 0 at the same 2 points, x equals 0 or y is equal to 0. Okay? So the only possible fit for both of them would be where they're both equal to 0, because you got to have both of the partials equal to 0, or either one of them not defined, and they're defined everywhere. So at 0, 0 is the thing in question. Okay? Now, that's the critical point. So 0, 0 is a critical point. Okay? Now, to determine whether that's a relative maximum or minimum, what do we do? F sub, no, we've already done it, yeah. F sub xx at xy. And actually now we could be putting 0, 0 in there because that's the only place we're interested. So why don't we do that? Save us a little bit of grief later on. We'll take advantage of all the space we've got. And what would that be? What is the partial of, the second partial of F with respect to x both times? 2y squared, right?
Yes.
Yep. Okay. And at 0, 0, this is going to be 0. And f sub yy at 0, 0, well, any place would be what? 2x squared. And at 0, 0, that's equal to 0. Okay? Well, what's your f of x? Yuck. F sub xy. Okay. The second partial of f, this time with respect to y, that would be 4xy, right? Now, just for funsies, and by the way, that would be 0, 2, but let's just go on and do the partial, the other cross partial, you might say, mixed partial, f sub yx, just to make sure we did it right. And what would that be? F sub yx, that would be 4xy. So they are the same. They have to be. Well, they're equal to 0, 2, okay, at 0, 0. Well, guess what? F sub xx at 0, 0 times f sub yy at 0, 0 minus f sub xy squared at 0, 0 is 0. That tells you nothing, nothing at all, okay? You can't tell if you have an extreme or not, and what it is, you can't tell a thing from that, okay? Well, with everything being 0, no wonder you can't. So, we either have to draw a graph, which I sure don't want to draw. Okay, they're really hard to draw. If you have a graphing utility, that might not be a bad idea to do. I just happen to notice here that's a minus sign in the middle here, and it's just way too big and thick. Okay, minus sign. Okay. Or some other means of evaluating this. Okay. Well, first at 0, 0, the function value is 0, 0, is 0 also. So when x equals 0, y is equal to 0, your function, or your z, is equal to 0. Okay? Now, what I would be tempted to do was go a little bit out from 0, 0 in any direction, but you can't be along x or y axis because everything's 0 there. But if you go out, say, 0.1 and 0.1, 0.1 squared is 0.01, and 0.1 squared is 0.01, and 0.01 times 0.01 is 0.0001. So guess what? They're going up there. And if you do the same thing in the other direction, plus 0.1 minus 0.1 still gives you the same answer. Minus 0.1 plus 0.1, same answer. Minus 0.1 minus 0.1, same answer. So they are going up around that, so that would indicate to me that 0, 0 would be a relative minimum. Okay? Just because you go a little distance away from it, but not along the x-axis or y-axis, because everything's 0 there, then you have a slight positive value. And anywhere you go beyond that, as long as you're not on the x or the y-axis, then you've got positive values there. Okay? So that means to me that the cross of the axes down here in the xy plane, theirs are always 0. And everything in between that are positive. From forever and ever and ever. Okay? So therefore, that's what it seems to look at like. And if you look at the figure on the page, y'all can't see it, can you? You don't, neither one of you have a book. Okay? Let me show you what it looks like. Then what I've been trying to describe at x equals 0, that's the y-axis, it's always 0. Y is equal to 0, the x-axis, that's always 0. 0, 0 is always 0. But everywhere in between there is going up. It's going up slowly at first, but then it goes quite high. So basically, big book, it looks like a, here is kind of how I would describe it. Let's picture you had, so here say is the x-axis along this line right here, and the y-axis along that one. And you take a sheet and glue them down along the x-axis and the y-axis. Glue it down, but then lift these portions here like that. And that's what it would be. Always trying to lift up here, but glue in place down there. So minimum all along those axes, but going up everywhere in between the axes. It has to be a flexible sheet because otherwise it would be, it has to be a rubberized sheet that you can pull up that way. Okay. Okay, conclude that each of those critical points everywhere along the x-axis and y-axis and the origin, of course, too, are relative or absolute minimum. Same thing we said. All right, let's move on to the next slide right here. Absolute extrema of a function can occur in two ways. First, some relative extrema can also happen to be absolute extrema. In this instance, in example 1, the f of negative 2, 3 is the absolute minimum of the function. See if we can see that again. It was not this time, it was last time. There's it. Okay. Yeah. Absolute minimum. Okay. That was last time. Okay. No, nothing ever. The only one extreme value, -2, 3, and that the value is 3, and everything beyond that is greater than that. So, absolute minimum. Okay. All right, so that's the first, absolute minimum. On the other hand, the relative maximum found in example 3 is not an absolute maximum. Okay, let's go back and look at, oops, there it was right there. Okay, let's clear all that mess out of the way. All right. Now remember, this is a saddle point here, so not either max or min. Here was a relative maximum here. But look here, not an absolute maximum at all. That takes off and goes far greater. Over here, yeah, it always stays less. But over there, whoo, it keeps going up and up and up. Okay? So therefore, it's a relative maximum, not an absolute maximum. Okay? Whoa, goodness. Okay? Second, the absolute extrema can occur at a boundary point of the domain. Okay? And we saw that before. When we have some type of domain issues there, you're, especially if it's a closed domain, in other words, the boundary values are part of the domain, then it could be your absolute extrema occurs there. Okay? Now that's all they say, and they don't show example 5. So let's go back and do example 5 here. Okay. Using this slide to death, I think. Find the absolute extrema of the function f of xy is equal to sine xy. Okay. On the closed region given by 0 less than or equal to x less than or equal to pi, and 0 less than or equal to y less than or equal to 1. Closed region in x and y. Okay? Where would we begin? We're looking for absolute extrema. What do we do first? Yeah, f sub x. And what would that be? Second? You say it is cosine. Cosine xy, but then you also have to do a chain rule in it. You see why? Okay. You did the derivative of the outer function, which was cosine. I mean sine. The derivative of sine is cosine xy. Same argument there. Then you take the derivative of this with respect to x, and that would be y. So that's the chain rule part. So it's y times the cosine of xy. Okay? Now, let's go on and do our other partial, which is f sub y of xy. And what would that equal? X times cosine xy. Okay. Now, what we're interested in is where they may be 0 or undefined. Well, they're defined everywhere, especially on that limited domain, okay, closed domain. Okay, so basically all we're interested in is when there's 0. So where are those functions 0? Obviously, one point is anywhere y is equal to 0, this is 0, right? Anywhere x is equal to 0, this is 0, right? So those will be both 0 at 0, 0. So that's one potential place, okay? That's one critical point, 0, 0. Another place they're equal to 0 on this limited domain. Where is cosine equal to 0? Where is cosine equal to 0? I'm going to have to talk with your trig teacher. Where's cosine equal to 0? No, sine is 0 at 0. Cosine is 1 at 0. Where is it 0? Okay. Where is cosine equal to 0? At what? Okay. No, sine is 0 at 0, pi, and 2 pi. All your integral pi. Sine is 0 at every one of those. Cosine is 0 at all the half pies. Pi halves, 3 halves pi, 5 halves pi, 7 halves pi, negative 3 halves pi, negative pi halves, all your half pies, cosine is 0. Okay, but we aren't doing any negatives here because both of those start with 0. So this would be x equal pi halves and y is equal to 1. Okay, that certainly would be 1, right? So that would be this one and both of those. So pi halves 1. Now it seems like there could be some more. Let's see if they are. Those are at least 2. Let's stop at those 2 for right now. It's basically anywhere that x, y is equal to x times y. This is ugly. Anywhere xy is equal to pi halves. Okay, that's the only place because anywhere outside of there it's not. Okay, so that means x is equal to pi halves over y, and certainly 1 would work, but if y was 1/2, that would work too. Pi and 1/2, because xy was that. So there's lots of possibilities there. Something in between, let's say 3/4 pi and 4/3. Oops. Two-thirds. Yeah. So there's lots of potential places like that. So there's an awful lot to look at here. Okay. But all we're interested in is the absolute extreme of the functions. Okay. All right. Now, it's wherever this is true. xy is equal to pi halves. All right. Now, if xy is pi halves, then f of xy is sine of pi halves, because xy is equal to pi halves, and that would be 1. Okay. Now, like I said, the other one was where xy is equal to 0, 0, and there the sign would be 0. Okay. So, f of 0, 0 is equal to sine of 0 times 0, which is sine of 0, which is 0. Sine of 0 is 0. Okay. Now, I see why they didn't show this one on the slide set. This is just sort of a talking through the situation here. All right. I'm going to just hang it up there because you have to look at the figure in the book, which is not a super one to look at, but it's saying a lot of the same things we just said here. Of course, it's 0, 0, 0. Everywhere along the y-axis is 0. Everywhere along the x-axis is 0. You're going from 0 to pi on x and 0 to 1 on y. Okay. Now, the other place that's equal to 0 is anywhere that x times y is equal to pi halves. Of course, when y is equal to 1, x is equal to pi halves, so that's a maximum. But anywhere along that line, and that goes to where the extremes of that is, I think, x equal to pi and y is equal to 1/2. There's that one there, and the other is x equal to pi halves, and y is equal to 1, which would be somewhere right about here. I guess that's that point right there. I can't hold that up any longer. So all along that ridge there, you have what we call the absolute maximum, because there you're equal to 1 and only there. You can't get any greater than that. Where your minimum, well, we already said the x-axis and the y-axis, but there's one more place, and that's this one here, where x is equal to pi and y is equal to 1, then x times y is pi, and sine of pi is 0 there too. So you can't get less than 0. Sine is positive everywhere on that. So it's 0 on the x-axis, on the y-axis, and then also up here at pi 1. Okay? Its absolute minimum along this line here is the ridge there from x equal pi halves and y is equal to x equal pi and y is equal to 1/2 back to x equal 1 and pi is equal to say that? X equal pi, I already said that. X is equal to pi halves, and Y is equal to 1. That would be that value right there, pi halves and 1. It's really hard to see on this. Again, trying to draw a three-dimensional graph on 2 dimensions, it really is hard to see. Okay. And that's how they do it. You can't find them all because of infinite numbers. That's the bottom line. All right, 13.8. Shoot. Glad to be through with this one. Any of the odds 3 through 7, they're all at Calc Chat, 7's at Calc View. Any of the odds 9 to 23, they're all at Calc, well, I would say 9 to 20, let's see. 9 to 19, they're all at Calc Chat, 9's at Calc View. Then they gave you graphs for 21 through 20 and 23. They're both at Calc Chat. Either 25 or 27, they're both at Calc Chat. Do 29 is at Calc Chat. Either 31 or 33, they're both at Calc Chat. 35 or 37, they're both at Calc Chat. Any of the odds 39 to 45, they're all at Calc Chat. 39 is at Calc View. Do 47 is at Calc Chat. 49 and or 51 should be at Calc Chat. Both of those were exploring some water issues, I guess you would say. Well, I don't know. They're dealing with things that are exploring concepts. Let's put it that way. I don't know why I say water. You know, they just have some values there. If they're at Calc Chat, follow up on them. If they're not, just whichever you choose to do. 53 should be at Calc Chat. You should be able to do that. There's a couple true false, 55 and 57. They should both be at Calc Chat. And that's the end of that. Now, 13.9 is applications of extreme applied optimization problems. Are you, or if you know if Mohammed's going into industrial engineering?
I have no idea.
What's that?
I have no idea.
Okay. If you are, 13.9 would probably be a good section to look at. And just flipping the pages here, here's Andrian Marie Legendre. That's a male name, even though Marie sounds like it's feminine. Adrian, I guess it is. They may not say Adrian, they probably say Adrian. But he is mentioned here. He would be a good paper topic. But because that's pretty specified type material, I'm going to say let's just skip it because we need to move on. That was Legendre was mentioned there. Then you have Lagrange multipliers, and again, that's named after the French mathematician Joseph Louis Lagrange. The other guy I think was French too.
That's what I did my paper on.
Huh?
That's what I did my paper on.
Lagrange or Legendre? Lagrange. Okay, I thought you did. Okay. Yeah, both of these were French mathematicians. This was sort of the height of France's economic and also intellectual peaks. They both lived about that same time, but there is Lagrange, and he did his Lagrange multipliers or Lagrange theorem. You can write on him his multipliers, his theorem, whatever you choose to. So anyway, there's it's all getting toward optimization theorem, which is mostly done, I think, or at least my impression, in industrial engineering, though you might have some applications in mechanical and some of the others, possibly even electrical. But let's just skip those two, and that finishes the chapter. I wish I had your test ready. I'll knock on wood, try to have it ready for Wednesday, okay? And let's move on to the next chapter. And by the way, if you haven't had enough exercises to do, there's some review exercises at the end of the chapter. This is on page 964. And basically, You can do any of these. I think in the back of the book, they give all the answers for these, but on the Calc Chat, it's still the odd number exercises. So 1, 3, 5, 7, 9. There's something there called the Cobb-Douglas production function, which if you want to write on that, you could, but you don't have to do it. It's an even problem. Number 11, any of the odds 13 through 17, any of the odds 19 to 25, any of the odds 27 to either 27 or 29, either 31 or 35, 37 or 39, 41, 43, 45, either 47 or 49, 51, 53, 55, 57, 59, any of the odds 61 to 65, 67, 69 or 71, 73, 75, 77, any of the odds 79 to 83, now, some of those other are pretty interesting ones to do, but I think they involve the sections I was saying we could skip, so you can skip from there on. There's a problem solving that Calc Chat has tutorial help for the odd number exercises there too, if you're interested. By the way, Heron's formula is mentioned. You probably remember that from trig, I hope, but if not, there it is again. You can write on Heron, and there's the Cobb-Douglas production function again. So there's that. So let's move on. I'm sorry I don't have your test ready. I had planned to be in the office last Wednesday, and I was going to, I probably would have gotten it done then. It turned out I had to leave Wednesday morning, so couldn't do that any further. So I'll try to get it done this afternoon if possible. Okay, discard that and move on to skipping 13, 9, and 10. We'll go on to 14.1. This will be the last chapter we do, obviously. We don't have much time. Let's get started now, and your final exam will be just what we cover in 14. We'll cover as much as we can in 14. And we have now, about 20 minutes to go, right? Okay, so let's get done what we can.
That was the last chapter was 13.
13. And we'll do 1 through 8 in it, sections 1 through 8. I'll try to get that test ready for you by next time. Okay. 14.1, or chapter 14, they didn't give you a slide on it, did they? Yeah, they did. Multiple integration. Okay. And 14.1 is iterated integrals and area in the plane. And I'm going to try to do this section as quickly as possible. We'll evaluate an iterated integral. Of course, we've got to define what that is. And we'll use an iterated integral to find the area of a planar region. So what in the world is an iterated integral? Okay. Boy, that light comes in right on the afternoon like this, doesn't it? Can you see okay? Yeah. Okay. All right. Here we have an integral going from the left. Oh, my goodness, it's 10 o'clock scholar. Here we go. All right. Justin's here. And did we lose him for good?
Yeah, he said he had to go to work.
Oh, he did that. I thought he just stopped out. I wasn't paying close attention. So here we have a function, an integral. The integral is taking just the integral of the partial of a function of two variables, x and y, but just the partial with respect to x, okay? And we're going from the limits are h1 of y and h2 of y. Notice there's no x's here because we're integrating over x, but there could be y variations there, okay? Now, if you do that, take the partial with respect to x, partial with respect to x, you're integrating with respect to x. This just gives you the function f of xy evaluated at these two boundaries, h2 of y and h1 of y. So in other words, wherever you have an x in there, you plug in h2 of y, and then that same thing, plug in h1. In other words, f of, instead of x, h2 of y, comma y, that was a constant, so that doesn't change, minus f of h1 of y, comma y, because you're integrating with respect to x alone. Okay? A little bit of a weird situation here, but hopefully it makes some sense there. Or if you're doing an integral of a partial with respect to y, where x is held constant, and you're doing the integration over y, this will give you f of xy, but then between these two limits of g1 of x and g2 of x, so you plug in the g2 of x for the y, so f of x, g2 of x minus f of x, g1 of x, and evaluate that. That then is your what they call iterated intervals. Note that the variable of integration cannot appear in either limit of integration. Okay? So if you respect to x, you can't have an x here. If you respect to y, you can't have a y there. Okay? It makes no sense to go the integral from 0 to x of y dx, because you're integrating out the x's here, so you can't have x in the integrand. Okay? So, I mean, it's a limit. All right. Here's an example. Let's see if we can go with it. Okay? We're integrating with respect to y only. Okay? So, let me get my pen back. Basically, since you're integrating with respect to y, we hold x constants. Treat x as this a constant. Just the reverse of what we're doing when we're doing partial derivatives, right? Now we're doing multiple integration. So we're integrating with respect to y. What is the antiderivative of 2 xy with respect to y? Antiderivative of this. No, not 2y. No. Okay. Integrating with respect to y. So this is the only thing you're integrating. You count the x as a constant, and of course 2 is already a constant. So what would be the antiderivative of blank y? Okay.
You teaching a class today, Dr. Fowler?
I'm teaching this class.
No.
You mean Dr. Bryant's class?
Yes, sir.
Yeah, he's teaching. He was here today earlier.
Oh, I'm looking like, because, they in my class.
Oh, I see.
Doing the rhythm and stuff. Wow, this is so hard. You got to do it backwards. I was
Yeah. Exactly.
I was tripping.
Yeah.
Let's see. I'm telling you, I was in the game.
Yeah.
All right, Dr. Fowler.
All right.
Yes, sir.
Okay. If you need to, rewrite it this way. Integral from 1 to x, or you can leave that stuff out. Because the x is treated as a constant, call that cy plus 3y squared dy. Just treat the x as if it's a constant. If that was your problem, how would you integrate this with respect to y? C is just a constant. That would be y. Integrate. Antiderivative. Second. Second.
I was thinking of IJK.
That's you're talking about as far as vectors. Yeah, this is a vector thing. This is just a scalar integral. Antiderivative would be increase the exponent by 1 and divide by that. Would be the this has an exponent of 1 already. Increase it by 1. 2. Y squared over 2, right? Isn't that antiderivative of y? Okay. So this would be c times y squared over 2. But your c is 2x. Okay? Well, 2x over 2 would just be x. So this would be, let me erase this if it's okay. Well, I don't need to write it again. Okay. All right. Now, y is the only thing you're integrating here. So that would be y squared over 2 times 2x. See, the 2x is a constant. Leave it alone. You only integrate the y part. You see that? Okay? And then the 2's go out, right? Plus, okay, plus the antiderivative of 3y squared. Second? I can't hear you. Yeah, 3 is a constant. What's the antiderivative of y squared? Second? You're differentiating. You're integrating. Antiderivative. Y what? Y what? It's already y squared. Second? Yeah, y to the third over 3, but then you had a 3 in front, and now the 3's go out. Okay, you're going to evaluate that from 1 to x. Okay? Now, so let me write that down again without the scratches in it. xy squared plus y cubed evaluated from 1 to x. Now these are values for y. Y equal x, y equal 1. Y equal x, y equal 1. Okay? So when y is equal to x, this would be x times, if y is equal to x, that would be, y squared would be x squared. So, right? So x times x squared would be x cubed plus y equal x, that would be x cubed, right? Okay? Minus, plug in y is equal to 1, that would be x minus 1. I mean, the minus is because it's the lower derivative. And plug in y is equal to 1, that would be 1. So this would be 2x cubed minus x minus 1. Do you see that? Sort of like he said, you're doing it backwards. You know, but here, just like when you're taking the partial derivatives, you're taking the derivative with respect to x, count the y as a constant. If you're taking the derivative with respect to y, count the x as a constant. Same thing here. Treat this x as you're integrating with respect to y, so it's just x is just a constant. So this would be 2x, that's a constant. Integral of y is y squared over 2, right? Okay. And 3 is just a constant. And integral of y squared is y cubed over 3. Okay, it just happens to be that's a 2, there's 2 in the denominator, 3 and 3 in the denominator, so that gives you that. Then when you go to evaluate, remember you're evaluating y's. So the y changes to x, the x stays x, it's a constant, right? And this becomes x times x squared, because y is equal to x, that's x cubed, plus y is equal to x, y cubed would be x cubed, then minus when y is equal to 1, so that would be a minus x, because y is equal to 1, and then the second minus is minus 1, and y is equal to 1, that's just 1. So there's our answer, I hope. Let's see what they got in the book. Oh, look at there, they got 2x cubed minus x minus 1. Okay? Let's watch them do it and see if they clear it up any. I don't know if what I was saying was making sense to you. Considering x to be a constant, integrating with respect to y only, then they didn't even show as much as I did. They just went straight to xy squared plus y cubed, which is what we got. And then you evaluate the y's at the values x, and then minus that evaluated when y is equal to 1. So that would be 2y cubed. Why they wrote it that way, I'm not sure. Minus, yeah, I guess they evaluated it first, minus x plus 1. So what they did was they did this with y is equal to x is here, so that would be x cubed plus x cubed, that's 2x cubed, minus, when y is equal to 1, that would be x plus 1. Okay? And then, removing parentheses, you have 2x cubed minus x minus 1. That's one way to do it. I think the way we did it was just as good. Maybe I see it better that way. It's up to you. Okay? So there was example 1. My goodness, they're going to do example 2. Well, wonders never cease. What did I do with my watch? Oh, I don't have my watch. It's in my pocket. All right, we've got a few minutes. Let's do example 2. Ha ha! This is a multiple integration. We're going to first integrate with respect to y, and then we're going to integrate with respect to x. Okay? All right. So let's leave this part alone, 1 to 2, and the dx alone. Leave that alone. Let's do the integral in the middle. Okay? Guess what? That's the same integral we saw before, isn't it? But let's do it again just to refresh our memories. What does that give us? Integrate this with respect to y. And what does that give you? 2, no, you were right the first one, 2x y squared over 2, which is xy squared, right? Okay? Plus, and what did that give you? Three y cubed over 3, so those go away. You evaluate that from 1 to x, which we already did, but let's do it again just for fun. Leave this alone, 1 to 2. Leave the dx alone. We'll get to that later. Let's evaluate that from 1 to x. So let's do the x first, and what does that give you? Second? 2y cubed, right? Second? Okay, we canceled out the 3's because we had a 3 in front and then it had a y cubed. So those 3's went out, those 2's went out. They don't there anymore. We're evaluating. Okay. I thought you had already done it here. Okay, when you plug in an x, this gives you x, because that x is a constant. Don't worry about it. And for y, because that's what you're integrating, you put y is equal to x. So it'd be x times x squared. That's 1. I'm sorry. You said 1. That's an x. Threw me off there. Why'd you do that? That's 3x squared. 2x cubed. 2x cubed. The first one comes from here. X times x squared is x cubed. And here we have a plug x in for y, you get plus x cubed. So that's 2x cubed. Now we plug a 1, but we're subtracting this now. That's in for y, because you're integrating with respect to y. So it'd be x times 1. So that's minus x, right? Because you're subtracting. Okay, minus x. And then when you plug y equal 1 in here, 1 cubed is 1. So it's minus 1, because again, it's the lower one. Now this is what we're integrating with respect to x. So, new problem here. This is what we got last time. We were going to integrate that from 1 to 2 on x. So what would that be? Integrate that with respect to x. 2x to the, second, you're integrating, antiderivative. You increase by 1. What's that? X to the 4th over 4. And the 2 will go in the 4 twice. So it's x 4th over 2, okay, minus, what would that would be? X squared over 2. And then the final one would be x to the 1. This is x to the 0, right? 1 is x to the 0, right? So increase by that 1, by 1, and you get that over 1, which is just what it is. And this you evaluate from 1 to 2. So let's review and see how we evaluate that. Well, let me write it a little neater here. X to the 4th over 2 minus x squared over 2 minus x. Evaluated from 1 to 2. I'm sorry? Okay. Okay, now, I just put the x to the 0 in here. That's 1, right? Okay. I was showing you how you integrate this antiderivative. You increase that by 1, making x to the 1, so minus x to the 1. Okay. Right, yeah, okay. Now, time out. What would happen if you took the derivative of this? 4 times 1/2 would be 2x cubed, minus 2 times 1/2 would be 1x, minus 1, right? Derivative of x is 1, right? So your antiderivative does this and make the derivative you get back there. So that's why it's called antiderivative. Undoes the derivative. That's what integration does. Now we're going to evaluate this from 1 to 2. But we plug in the 2 first, and what would that give us? 2 to the 4th is? Say again? You're plugging in for x. This is x equal 2 to x equal 1, right? Remember how to do? Yeah. Definite integrals. So 2 to the 4th is? Second? 2 to the 4th. You plug in 2 for the x. 2 to the 4th is? Is what? 2 to the 4th. Yeah. 2 times 2 is? Times 2 is? Times 2 is? 16. Is that what you said? Oh, you did. I couldn't hear. Okay. 16. But 16 divided by 2 is? Because you got to do it in the denominator. 8. Okay. Minus 2 squared is? Divided by 2 is? 4 divided by 2. 2. Okay. Minus 2. Right? Plug in x equal 2. Right? Now we do a minus plugging in 1. 1 to the 4th is? One to the 4th. 1. 1/2. Okay. Now we do a minus because it's the lower integral, but you have a minus there, so minus times minus is plus, and there we have a plus 1/2, right? And then minus a minus is plus 1. Well, these two add to 0, and you have 8 and 9. 8 and 1 is 9, minus 4 is 5. Is 5 the answer? Yeah. What's that? Okay. Right here. Okay. You start with this thing plugged in here, right? 2 to the 4th is 16, divided by 2 is 8. Minus, that's where that minus came from. 2 squared is 4, divided by 2 is 2. So that's where that came from. This minus is that. Minus, when x equal 2, that's 2. Right? Then, when you're plugging in the bottom numbers, it's the opposite of that. So it's a minus 1 over 2. 1 to the 4th is 1. So that's a minus 1/2. And then minus, a minus is a plus. 1 over 2 is a plus 1/2. And then minus 1 is plus 1. Okay? And then add your positives, 9. Subtract your negatives, minus 4, positive 5. Okay? That's definite integration. F of B minus F of A. Okay. Now, let's see how they did it. And they start by using the result of example 1, which I was starting to do, but I thought we needed to practice that a little bit more, because this was the same function right here, that same integral that we had in example 1, and it turned out being this. So I want you to do it again just to refresh your memory, or to restart your memory, or to start your whatever. So then we got this, and then when you integrate this with respect to x, that goes up by 1. 4 divided by 4, so it's 2x to the 4th over 4, which is 1x to the 4th over 2. And this becomes minus x squared over 2, and this becomes minus x, right? That's how you do your antiderivatives. Okay, and then you evaluate that from 1 to 2. And they just skip to the chase and do evaluate all this at 2, that would be 8 minus 2 minus 2, that's 4, minus 1/2 plus 1/2, that's 0, minus a minus is plus 1, minus a minus 1 is plus 1, 4 plus 1 is 5. Now if you see that better than the way I did it, but both ways you come up with 5. All you're doing is evaluating first at 2, then subtracting the evaluated at 1. So that's what they're showing you. Evaluate this at 2, that would be 16/2, which is 8, minus 4/2, which is 2, that would be 6, minus 2, that would be 4. That's where that came from. Minus, because you're doing your bottom number here, now evaluate all this at 1. 1/2 minus 1/2, that adds 0, minus 1. So minus a minus 1 is plus 1. However you want to do it, that's the answer there. All right. Oh, my goodness, I looked at my clock wrong. Yeah, we've got quite a bit of time left, right? What time is it? Oh, we're supposed to be through. Sorry about that. I misread my watch. Sorry. Yeah, y'all should be in physics class, shouldn't you? Let's see if we got enough to do any homework exercises. I think you can do any of the odds 3 through 9. They're all at Calc Chat. 3 is at Calc View. I think you can start doing any of the odds 11 through, 27. All of them are at Calc Chat. 15's at Calc View. If some of those get to be a little too much, hang on and we'll do some of the rest of those later. Okay? All right. We'll start the next time on page 971. I'll try to have your test ready for you too. Which means try to get, if you haven't done your paper, get those in. I think both of you have done yours, right? Okay. And then if you haven't turned in the first test, which I'm trying to figure out now whether you have or not. Yeah, I think both of you have turned in your first test. That's great. The second test, though, neither of you have turned in. Huh?
I'm just stuck on the 10.
Okay. Well, come see me if you need to. All right. So I'm going to